Hello and welcome to Toddcast number 7. Uh, if you've been following through all of these, we've done a lot of structure information, looked at bond angles, bond lengths, hybridization, shape, various features of a molecule. Now we're going to start looking at interactions between two molecules. So we briefly mentioned something called polarity in a previous podcast, which represents a scenario where you have unequal sharing of electrons within a bond. And if you share unequally, that means one is going to end up with a little more than it should, one's going to end up with a little less. If you have more of the bonding electrons, you have more negative, you're going to be partially negative. And if you're giving away too much, if you're other atoms taking it from you, then you're going to lose some negative, you end up with a partial positive. The bigger the difference in electronegativity, the greater this discrepancy between electron distribution, and the bigger the dipole moment. So we will look at the impact that has. So intermolecular forces are not actually covalent bonds. So within a molecule, within the structure, we worry about covalent bonds, but between, we worry about what we're going to call intermolecular forces or intermolecular interactions. There's going to be three that we will have an interest in. And I'm going to define them one way that may be slightly different than the textbook, but at the end of the day, it's all the same thing. It's just what we're focusing on. And so I think we all, no matter textbook writers or other teachers, myself, all will agree a dipole interaction, dipole simply represents two poles for electrons. It's excess of electrons or short of electrons, which means a minus plus. So electric dipoles are ones with a plus and a minus. A plus attracts a minus. So if you have a molecule that has one side, it's polar, it has one side that's partially positive. So let's say I have some molecule with a delta plus on one side and another molecule that's delta minus. They can form some sort of interaction, some sort of attraction. And so let me consider the following. I'm going to do something called chloromethane. Chlorine is more electronegative, so it will carry a delta minus. This will carry a delta plus. They will line up in a way where the structures will prefer to be lined up like this, where the delta plus is near the delta minus, meaning this molecule, if it lines up this way with the Cl pointing towards the right, then its neighboring molecule will be induced, or it'll find it favorable to put the chlorine on the same side on the right, so that the delta minus of one side can interact with the delta plus of the other. It's a relatively weak interaction. It's weaker than a covalent bond, so they're easily formed and broken. But what happens is you have to put energy in to break it. So it takes a lot of energy to break a covalent bond. It doesn't take so much energy to break an intermolecular force. So really low temperatures, freezing temperatures for a given molecule, meaning if I lower the temperature below its melting point, its freezing point, then this interaction will be strong enough that relative to the available energy, the energy can't break it, and it'll form a crystalline structure, form a lattice. When you give enough energy, it'll weaken it so they can now break and reform, and forms a liquid. And then if you raise that temperature high enough, you're eventually going to get to something called the boiling point, where you can break the intermolecular forces completely, and this molecule can fly off and be in just the atmosphere, independent of all other molecules. So there's going to be a correlation between intermolecular forces and the melting point and boiling point. So the higher the melting point and boiling point, the more heat, the higher the temperature you need to break the intermolecular forces. So strong intermolecular forces will result in higher melting and boiling points. Weak or minimal intermolecular forces result in very low boiling points. So helium, for instance, lowest boiling point we know, down around 4 degrees or 4 Kelvin. It has so little attraction between neighboring atoms that it takes hardly any energy at all to break the intermolecular forces and boil it at around 4 degrees. Okay, hydrogen bonding. This is one that will pop up repeatedly in biology. And so I want to make just a little spiel that I'm going to make a few times over the course of all these podcasts. And that is organic chemistry, I find to be an absolutely beautiful subject, but the reality is to get the most out of it, you have to know how to apply it. And so all the tangents you run into in various classes are actually, if you look at it the right way, great learning opportunities of the application of how it applies to other systems and other sciences. Most of the interesting applications of organic chemistry are found in biology. So without biology, organic chemistry would not be as enriched a study, wouldn't be as interesting, and honestly wouldn't be as useful. If it wasn't for needing to make biological molecules and understand biological molecules, organic chemists wouldn't have jobs. The flip side of that, biology cannot be understood without knowing the core organic chemistry of how molecules interact. So if you truly want to study biology, you have to understand uh, intermolecular forces, organic concepts, just organic chemistry on the whole. So they feed into one another. So you're going to see little by little as we go into more and more OChem, you're going to take on more and more OChem examples and bio, and hence the field biochemistry sprung out, where the two fuse together. Okay, hydrogen bonding. Hydrogen bonding is stronger than a dipole-dipole interaction, and it has a very slight covalent-like component to it, which means orbitals have to be lined up in a certain way. So it's almost like a dipole interaction where you have a little bit stronger interaction. So let's say here's my water. Water has a delta minus on the O and a delta plus on the H. So if there's another water molecule, I'll draw it in a different color, and its lone pairs are lined up the correct way, such that the delta minus is close to the delta plus, can actually form, if they're lined up in a relatively straight line, can form a very strong H bond, which is why water has an abnormally high melting point and boiling point for something its mass. Its mass is only 18 grams per mole. Comparable molecules like methane and ammonia are gases at room temperature. Water is a liquid. It has such strong hydrogen bonding that it takes so much energy to break it into the gas phase that at standard conditions, the conditions we live in, water most naturally is a liquid. It is the lowest molecular weight liquid known, and that's because the intermolecular forces are so strong. And you've studied properties of water, I'm sure, over and over, but this key thing is hydrogen bonding. Not to get too philosophical, but it is kind of the secret of life. This is how life on our planet, water-based life, works because of the hydrogen bond. Okay, notice I used oxygen, but I want to point out you can get hydrogen bonding, nitrogen, oxygen, fluorine. So if you recall that hydrogen bonding occurs with no F, NO, and F, then on your hydrogen bonding exam, you will get no F. You'll get a much better grade. So if you know hydrogen bonding is when H is bonded to an N, an O, or an F. It's got a big enough plus to accept the lone pair from whatever atom donates to it. And typically it is NO and F of another molecule from a hydrogen bond. That would mean hydrochloric acid does not form hydrogen bonding. Compound known as a thiol, where hydrogen is bonded to a sulfur, does not form hydrogen bonds. So weird as it may be, compounds like H2O is a liquid at room temperature. H2S is a gas, even though it is heavier, and by being heavier, it should take more energy to remove one molecule from the liquid. It takes much less energy, so it turns into a gas. Hydrogen bonding causes water to be a liquid. Okay. Teaching a lot of GChem and biochem with this. London dispersion forces and LDFs, as some people will call them, any way you want to picture it, it's a brief interaction. So a really good analogy, two ships passing the night. They talk about these terms. So let's say there's two ships passing in the night. There are two ships, one going that way, one going that way. For a brief moment, if everybody in this ship goes to this edge and starts to look at this other ship passing through the night, it will tilt a little bit. And these people repelled by that repulsion will go to the other side and they'll tilt. So just for a brief moment as they're passing, they interact. Not the best analogy, that's mass distribution. But if we talk about charge distribution, I have a delta plus delta minus, and I'm going to put a subscript T because it's temporary, and a delta plus and delta minus. Sorry if I'm writing in a sort of weird way. I don't know if you could detect the background here, but I just went through an earthquake. Wow, okay, going to keep going. These temporary interactions, so it's the same thing as a dipole-dipole interaction, but just short-lived, just as they pass by. So they're considerably weaker. We justify them in a whole bunch of different ways, but basically, they're just contact. When two surfaces come near each other, they will find a way to attract one another. Because they're temporary, it's short-lived. So really, really good example of intermolecular forces. Glue, super glue is a covalent bond, strongest bond of all. Super glue is something that doesn't come apart. Water-based glues like Elmer's glue are usually hydrogen bonding. So glues, when they get wet, don't stick as much. When they dry out, they stick a little bit better because all the water evaporates away, so they form hydrogen bonds with themselves. And then very weak adhesives start to take on the other properties. So kind of a cool little thing if you want to design an adhesive, permanent, semi-permanent, weak, and then just like a sticky note, you would change intermolecular forces between the materials. Okay, so those are definitions. Now for the examples, this is a molecule known as acetone, and it's also 1, 2, 3 carbons, so prop, unknown, so propanone, meaning it's a ketone. It's going to be a functional group we'll learn. I plan on just every time I run into a molecule, giving the nomenclature of it, because multiple exposures help in solidifying the information. But we have this molecule because carbon is less electronegative than O, I think. I can't remember, so I asked my good friend Fonkelbrish. Where O is more electronegative than C, so that'll be a delta minus, this will be a delta plus. Hydrogen bonding, it has to be with an N, O, or an F. So H's on carbon here and here cannot hydrogen bond, but H's on nitrogen can. And then London dispersion forces, they're always there. So it's kind of a weird notion that we only consider them for this molecule, but they're always there. This molecule and this molecule will have London dispersion forces, but they're so weak that they get overwhelmed by the other ones. So if you were polar, you have polar interactions. If you have hydrogen bonding, you are polar, but you have a stronger interaction. So if you will, anything that has hydrogen bonding also has dipole and London dispersion forces. So it's going to have the strongest interactions. Anything with dipole but not hydrogen bonding has dipole, dipole, and London. And molecules that have no dipole and no hydrogen bonding just have London dispersion. So they have a weak force. This one has a weak and a medium. This one has a weak, medium, and strong. So hydrogen bonding is your strongest interaction between molecules. Okay, so as mentioned, delta minus delta plus because O is more electronegative. This one, delta minus delta plus, but also you have delta minus and delta minus. So H's have delta pluses. So I'm going to show this molecule in more detail towards the end of this. It's a compound known as urea, very common in bio. You find it as a component in the medulla or in the bone capsule of your kidney for filtering. So it sets up a gradient to help reabsorb whatever you're trying to reabsorb. So usually water in this case. But you have urea gradients, which help with this. Biologically, it does a few other wonderful things we'll talk about. But because it forms such strong hydrogen bonds, it can reabsorb water very readily. And then everything here is carbon and hydrogen. So there are no hydrogen bonds that can form because there's no NO or F. And carbon is about the same electronegativity as carbon. Carbon is carbon. H's are roughly the same. So essentially no intermolecular forces. Okay, so as mentioned, acetone would want to line up next to acetone, next to acetone. So carbon plus would want to be near O of a different molecule. So if I were to draw this, I'm going to just be lazy and draw it like this. I would see this molecule wanting to have this delta minus next to that delta plus. Okay, hydrogen bonding wise, I would expect that this urea, we'll leave the one urea there, and I'm going to erase the lone pair on top and put it on bottom for easier drawing. That will end up forming an H bond, which I represent as a dashed line to an H on a nitrogen connected to another urea. So a dashed line between two atoms. And you want the orbitals to line up the correct way. So I should have drawn this linear, but I just wanted to line it up with according to lone pair. So if this orbital's here, that orbital's got to be there. And this nitrogen here have to be a straight line from that N to that H to that N. But did draw it well. And then this one has no interactions of note other than the delta minus and delta plus you get briefly when they pass. So I don't bother drawing those in. Okay, so as mentioned, let me go back to clearing all this and say that this is weak, this is medium, and this is strong. These are all roughly the same molecular weight, and the reason I bring that up is heavier molecules take more energy to lift. So therefore, they will have just higher melting points and boiling points naturally because of their mass. Just to make sure, let me make sure I know the masses. Carbon, 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 36. Plus that is 42, plus 16 is 58 grams per mole. Carbon 12, 14, 14. So 12 plus 28 is 40. Plus those be 44. And 16, that's 60. So that's really close. Molecular mass. Here I have 4 carbons, so 48 plus 8, so 56 grams per mole. So they're essentially the same mass. So mass being equal, boiling point depends on molecular weight and intermolecular forces. So the masses are all comparable. So the strongest forces should have the highest boiling point. So it ends up urea is a solid at room temperature. So it's a higher melting point than room temperature. It's relatively high. And it has a really high boiling point. Boiling points are always higher than melting points. Acetone is a liquid. For us, you may have dealt with it as a, I don't know, glue remover, polish remover. It's a really good solvent to remove things. Its melting point is negative 94.6, which room temperature is much higher than. So it's going to be a liquid because we haven't quite reached the boiling point. So it can't turn into a gas, but it will have melted and not be a solid. So this will be a liquid at room temperature. This will be a solid at room temperature. And then this molecule, the room temperature is above the boiling point. So this one is a gas at room temperature. So the phase you're in at room temperature can help predict how strong the forces is. Solids must have strong forces because they're being held together in a lattice. Liquid still has forces, but not as strong because they're free to break and form as they move around. And gases, really weak forces because they completely break them and go off into the surrounding atmosphere. So we're going to use boiling point and melting point to explain the phenomenon, and then we're going to work the other way around. We're going to give you molecules, and based on what you recognize for the structural features, what you predict their boiling point and melting point relative to other molecules. Sounds arduous, but it's actually kind of fun. So think of it kind of like an OChem game show. Okay, so hydrogen bonding. Want to look at this in a little more detail. Again, you have a delta minus on an oxygen, a delta plus on hydrogen. This over here can be anything. So I made this molecule known as methanol. 1 carbon, so meth, alcohol, so enol. This H can interact with this O, or this O can interact with this H, depending on how they move around. So within solution, they're tumbling, they're spinning, they're moving around, and let's say they get close enough, if they happen to line up, if this line is in line with this line, that lone pair there is in line with that bond, then you can get that covalent bond and this hydrogen bond. And again, you have to have the orbital lined up in a way that interacts with the hydrogen orbital for the best possible H bond. You can have bent H bonds, they're not as strong. This is much better. So these molecules will tumble around, they form an H bond, give enough energy, they'll break, move around, form again. So in a liquid, molecules are always moving around, but they briefly stop to form an H bond, then break again, form a different H bond, and so forth. So H bonding, covalent bond, is collinear with hydrogen bond in an ideal scenario. Okay, much stronger than this interaction. So this is fair game, but you have one H bond. Urea, which we mentioned was NH2, C double bond O, NH2, has 1, 2, 3, 4 lone pairs that can be shared, and 1, 2, 3, 4 H's, which means it can form 4, 5, 6, 7, 8 hydrogen bonds for only having 1, 2, 3, 4, 5, 6, 7, 8 atoms. It can form 1 H bond per atom. Water, if I had H2O, can form 2 H bonds with 2 lone pairs, but 2 H bonds per 3 atoms, which means not the same. 8 over 8, 1 H bond per atom. This one, if it was water, would be 2/3 H bond for every atom. So because it's so strong, it is the strongest H bonding molecule we know. And there's a cool application we'll get into later in this because it forms such a strong one. But the interaction here, again, this lone pair needs to be lined up straight with the H, this lone pair with the H. It can also form an H bond down here, down here. This can form one, let's say, coming out of the plane. But you can get a very massive crystalline network between all these H bonds. And if you've taken any bio classes, again, H bonds, I had a biochem teacher who mentioned 1,000 strings make a rope. And that's interesting. Or 1,000 threads can make a fixed string or rope. And that analogy didn't make sense at the time. It was one of those grenade analogies. It went off later in my life. And when it went off, it's like, whoa, that makes so much sense. H bonds are individually very weak compared to covalent bonds. But for a compound like urea that can make so many H bonds, it's quantity over quality. So it can make 1,000,000 H bonds. Those may be individually weak, but all those together can hold the molecule tightly, which is why pretty much every biostructure of interest is held together by H bonding, not one H bond, but multiple H bonds, because a whole bunch of threads eventually will make a rope. And you can hold together, rope can hold things together really, really tightly. So this structure, this orientation, know this for bio. Which brings up the interesting biological spoiler alert. Urea is so good at H bonding that we actually use it to destroy or denature the compound. So you may have learned somewhere along the line that amino acids form proteins. So here's one amino acid, here's a second amino acid. And so amino acids have an amine, a carbon in the middle, and what's a carboxylic acid. But when it forms a protein, it loses the OH that was on the amino acid here and the H that used to be on the N. And so this represents a polypeptide. And so I've drawn, or only drawn 6 in a line. Proteins are significantly longer than that. But proteins can actually, as they fold around and twist, their carbonyl of the peptide can interact with the hydrogen bond and connect to an H on an N. The only thing is, again, I mentioned that they want to be in a straight line. This is not a straight line. So hydrogen bonding in biochem is not as strong as hydrogen bonding in a free molecule within a liquid. So if it's a solid forming this, which is absolutely imperative because a lot of our biomolecules have to form a structure, then denature, renature, denature. They constantly open and close to carry out whatever function. So if the bond was too strong, the protein couldn't unfold to take on, like an enzyme, for instance, a protein-based enzyme wouldn't be able to unfold and create an active site that's useful. If it had no H bonding, it wouldn't come together. So if they can form H bonds that are relatively weak, it can form and break continuously. It can open up and do what you need to do, bind the substrate, close up, kick out the product. Okay, that said, urea forms amazingly useful H bonds, and because it's a small molecule, it's free to line up the right way. So it's going to form better H bonds with protein than Protein will with itself. So if I add urea, this H bond right here, protein's going to go, forget that. Why settle for this O that's just really weak and not lined up the right way when I could potentially have urea? So it will actually start unzipping the protein. We denature it. So if we want to study a protein, if you want to analyze a protein, a lot of times you have to, like, instead of a tied up string in a knot, you have to untie it, stretch it out to analyze it. So one of the first things we do is we add urea to break the hydrogen bonds within the protein. And so now those same amino acids that used to be here, the first one, second one, third one, fourth, fifth, and sixth, are now bonded to a urea up here and a urea down here, urea up here, urea down here. So these ureas can come in and line up and they're free to move around. So I put them in the same position as before because it can rotate, it can make a stronger one, rotate, it can form a stronger one. It can line up in a way where the H bonds are stronger. And so the protein will give up its H bonds to either another part of the protein or another protein if it's a dimer. But because of this, urea is used to denature proteins. It also means if you're doing bioresearch and working with urea, be really, really, really careful because it denatures you. Just fun thought. Okay. Other applications, you definitely have learned base pairing. So adenosine to uracil. So again, the difference between RNA and DNA is just a methyl group versus a lactomethyl group. When considering uracil thiamine, not going to go into it here. This is not the class for that. But whether I'm doing DNA or RNA. So if I'm doing RNA, for instance, as opposed to DNA, then I'm going to have the same basic pairing. And if I have a CH3 group coming off somewhere else, it doesn't really make a difference. Okay. But one of the things that for whatever reason they want you to know is that there are two H bonds when A connects to T or A connects to U. So A to U in RNA, A to T in DNA, or G connects to C. It forms three bonds. So this is a stronger interaction than this. So that may or may not have an impact on DNA building. It might have more of this pairing than this pairing as a consequence. Structural analysis may be impacted because it's harder to break this one than this one. But those are things you will learn in bio. I want you to at least think about that. The two H bonds not as strong as three. You also have to memorize, for whatever reason, purines and pyrimidines. I'm not going to be as into that as I should be, but purines have the double rings. Pyrimidines have just the one. Pyrimidine is a compound that we're going to run into in OChem a lot, where we have a six-member ring like this with one nitrogen. So that's where it comes from. Mnemonic, I still remember from, gosh, a gazillion years ago. Pure silver, where purines are Ag. Pure silver. So purines are A and G, which means the other two, T and C or U and C, are your pyrimidines. So you have to memorize it. But major part of bio. You're going to learn this over and over and over when you study DNA, RNA, protein folding. This H bonding concept is massive. Okay. H bond is highly directional, forcing RNA and DNA to bend into a certain orientation, which causes the foundation between base pairing is why it must form a double strand in a very specific, I guess, distance orientation. There's so many revolutions per peptide strand. If that, I mean, basically you'll learn the details of how it spirals, how many base pairs can be found in one complete turn. Okay, not a bio class. Solubility and miscibility. The terms are really similar, but enough different that I want to emphasize it. Solubility is when you're going into a different phase. So a gas is said to be soluble in a liquid, or a solid is soluble in a liquid if it dissolves into it. And if they're similar in properties, then they will dissolve in. Miscibility comes from the word mixing. So you mix things of similar nature, which means a liquid is mixing into another liquid. So miscibility is mixing, solubility is dissolving. So just subtle differences. But they're basically the same scenario. The solute, which dissolves into the solvent, if they're similar in properties, it'll have high solubility or high miscibility if it's two liquids. And if they are different in their properties, then it will be relatively insoluble. We will go over this so thoroughly in lab that I'm going to kind of, I don't want to say blow it off, but just not go into as much detail in lecture because it is a lab-driven phenomenon, but it is so critical in lab, knowing exactly what dissolves into what. So water is highly polar, so polar compounds will dissolve polar molecules. Polar solvents will dissolve salts, for instance, something very charged, something very polar. Non-polar, so we looked at alkanes, the only things that only have London dispersion forces, cannot dissolve salts. They're too different in property. So salt is not soluble in oil, but it is soluble in water. This is something you've learned in life. Really, really cool interaction of this. Our cell membranes, and just the interaction of like wax beads or water beads on a wax surface, because water doesn't want to interact with wax. There's no intermolecular forces that are in common. Hydrogen bonding for water, whereas in wax, you only have the London dispersion. So water, rather than interacting with wax or oil or the lipid, instead, what we're going to see is water will prefer to interact with water, and so it'll form its own little bead. This is something we take advantage of in so many aspects, commercially, biologically, very useful. So wax is what's known as a carboxylic acid derivative. So this is part of a carboxylic acid. When you have a long carbon chain here and a long carbon chain here connected to a double bond, carbon double bond O and a single bond O coming off, this, I want you to just remember this phrase, ooh, it's ester. Very exciting. So, ooh, there's two O's, it's ester. It's called an ester. Esters can have varying properties depending on the carbon length, but one of the things they can do is they form this long lipid chain and lipid chain. They have these long chains, so even though London dispersion forces are weak, when you have this long of a chain, you're gonna have a lot of contact, so a lot of interaction, so it gets more substantial. So the more contact area, the more surface area, the more points of interaction on a molecule, the greater the intermolecular force, the greater the London dispersion forces. Okay, so wax, typically long alkyl chain on an ester. If the chains get even longer than here, then it goes from being a soft wax to a harder wax. So a lot of the coating we put on pills is like this. It ends up that we can hydrolyze it and break the wax on that pill off. Candles can melt enough temperature to start disengaging, then this thing can catch fire. So, but typically, the longer the chain, the harder and less water interactive it's going to be. And then finally, cannula wax, the longest of all. You typically use this, Kamumba, sorry. You typically use this as an industrial wax to, I guess, put on a surface to protect it, ultimately waterproof it when you layer things together in a commercial processing. So I don't know, just the interesting fact of this. So they're all water insoluble because these long alkyl chains, these long non-polar carbon chains. Okay, so waxes typically made from esters, which is two long carbon chains. So just what it says there. Okay, now what we're going to learn is a cell membrane is exactly the same concept where you have these long chains, but you have multiple esters on this on a carbon backbone. So we'll talk about that a little more detail here. The intermediate point I'm going to make is if you don't have an alkyl chain, So in the previous example, instead of an O minus, sodium plus, we had another long chain. And again, these represent carbon, 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 and so forth. Long alkyl chains would make it a wax. But as soon as I get rid of one of those sides and make it polar, now we have an amphipathic situation. So amphipathic is where amph meaning both, pathic means pathologies, nature's properties. You have one end, a lipid, which means this is oil-like and non-polar. The other side, you have ions, which are very water-friendly. So you'll learn terms in bio known as hydrophobic and hydrophilic to describe those ends. So hydrophobic tail, ionic or hydrophilic head. And what happens with these then is if you interact with water, the ones that are negative will want to interact with the water. So this is from the water layer. The oil side wants to go to the opposite. And so on a surface, we have a soap. So if you're trying to wash something in an oily way, the oil can dissolve into this part of the region, and this carboxyl head, this ionic head, will want to go in the water. So if the water flows away, it'll take these molecules, which in turn will take the oil with it. So we use this as a soap to try to remove lipids from a surface that we have. So soaps drag the oil away or the lipids away from whatever we're trying to wash by filling them in these tails, which are connected to this, like covalently to the carboxylic acids that get sucked away in the flow of the water. Okay. So aggregated hydrophobic tails is what it's called, meaning all these line up a certain way. So you get this giant layer of lipid connected to the water. So these lipids have to flow where the water flows. Okay. Detergents, and I still do not know who made the decision that we're going to call essentially the same thing a different term, but for whatever reason, when it's a carboxyl group, a carbon, we call it a soap. When it's not exactly a carbon with a double bond O, this group, which means it could be an amine with a positive end, it could be a sulfate, could be a phosphate. It's anything except for carboxyl, we call it a detergent. I will never test that, but just to be complete, I want to emphasize the fact that carboxyl N soaps, everything else we're going to call detergents. So detergents are sulfates, amine or ammonium salts, and so forth. Okay. Lots of information being thrown at you. This is, I think, where we're going to get to what I find that perfect bridge between bio and chemistry. So we mentioned before the polar head, that was that C double bond O with another O coming off in a negative, and then the alkyl or hydrophobic tail. Typically, fats that naturally occur are even numbers. They're made from acetyl-CoA, a two-carbon molecule. So if you add 2 to 2 to 2 to 2 to 2, et cetera, to make a longer molecule, it's going to be even numbered. One is going to be their carboxylate group, which means if one is there in the even number overall, then there's an odd number of carbons in the tail. The one we just looked at was the C double bond O with an O coming off with one, and there were 11 others for 12 carbons total. So naturally occurring fats typically, not always, but typically are even numbers, linear fats. And there's going to be different lipids we make in our body. So I want to be careful to not say they're all this way, but for ones made from acetyl-CoA, without any modification, they should be an even number. So if we put them into a water environment, then what you're going to find is the polar head wants to be on the outside where you're touching water, but all the alkyl tails, instead of forming like a layer like we saw in the last one, they start pointing to the middle. I only show 2 dimensions here, but it actually is 3-dimensional, meaning that it could be coming out of this plane towards you. And so it's sphere-like. They're not exactly a sphere because they don't pack perfectly, but it's kind of like, I don't know, a gelatin capsule. If you've ever seen a vitamin E capsule, that sort of shape, somewhere between spherical and an oblong spheroid. And again, I'm going to show two dimension, but the advantage of a micelle is if I want to extract out a lipid soluble molecule using water, just like I mentioned in the soap example, the polar head is stuck in the water. So if the water flows, it drags the polar head, which drags the hydrophobic tail, which drags whatever else is dissolved into it. Micelles form in this sort of way in water, where you can shuttle a lipid in there. Interesting food for thought, literally food, and we're going to think about it. When you take a molecule into your body orally, you consume it, it goes in your stomach. The stomach is a water-based environment. It's going to pass through the pyloric sphincter into the small intestine, where it's going to be processed from a macromolecule into a smaller chunk. That smaller chunk is going to be absorbed and go into the bloodstream, which is also water-based. But it eventually has to get into the cell, which means it has to pass through a lipid. So no matter what, every molecule we consume is either an oil in an unfriendly environment, has to get through our stomach and our bloodstream somehow, and then it's going to be happily going into the cell membrane, a lipid environment, or it's water friendly, hydrophilic, like a salt, that goes into the stomach easily, goes into the duodenum or the small intestine fluids easily, crosses into the bloodstream easily, but you cannot get it into the cell very easily. You have to have a shuttle molecule or something else. Micelles, if you can visualize this, it's a giant water molecule vesicle here that's water soluble because of the outside, but it has a pocket on the inside to shuttle. So vitamin E is a perfect example. Have you ever seen vitamin E? It is not purely vitamin E you're taking that capsule. You're also taking soap. So the soap you have in here is forming this. The vitamin E is, let's say molecules are in here, 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 and here. This little micelle is overall water soluble. It can travel into the bloodstream. Once it gets to the cell membrane, it can turn inside out and deliver that vitamin E to the cell membrane. So it's a shuttle. Micelles shuttle lipid-soluble molecules into a surrounding water-friendly environment. If I put it in a lipid environment, it turns inside out, puts a lipid on the outside, and tries to get the charged species in the middle where water will be. So micelle is a sphere or sphere-like, sphere-esque collection of all these aggregated molecules that can transport lipids in the center in an overall water-friendly environment. Okay, so hopefully this seems okay. This makes sense. Okay. What you've learned at some point, if you've taken enough bio, is that we have so-called cell membranes. Not a cell wall, but a cell membrane. And it is, you've been told it's a lipid bilayer. And so it's hard to see in here, but you have two of these molecules, one here, and then flip it upside down, and one here. And so I've drawn what is a pretty ideal structure. Reality is it's not going to be quite that perfect, but you have this. So if you want to get something, let's say sodium plus, from here into here, it's going to be great here and great here because that's water-based environments. But getting through here is going to be really hard. So what you perhaps learned in bio is that we form channels. So it's going to be a protein channel made of something else. So then that means sodium can't go through there. So forget that path. Has to go in through the channel. So our cell membranes have to have channels. Okay. Bigger molecules. Glucose, for instance, way too big to go through this tiny little pathway. So a lot of times what they'll have is they'll have a giant transporter molecule. Where the glucose combined here, it turns itself inside out and then spits it out on the inside. So sometimes you'll find that in the cell membrane. And so, cell membrane. And so you have these different pathways to get those molecules in. Lipids, this usually is their end game. They just want to be here. So micelle will come and deliver it. The micelle gets here, the micelle will interact with here, it'll turn inside out and deliver the molecule to the cell membrane. Steroids work in that way, for instance. So if you've ever heard the term LDLs, low density lipoproteins, those are basically very large esters. They have the protein on one end, lipo mean the lipid end. these molecules aggregate like a micelle, and they can transport molecules such as cholesterol through the bloodstream. So high cholesterol and high LDL go together because cholesterol can't move naturally through the body. You need the micelle to help it move through the bloodstream. So unfortunately, high cholesterol means high transporter. Transporters, though, can deliver it to the cell membrane. It does whatever message it needs to give, and then gets released. The micelle picks it up, moves it to the next cell, next cell. And so we also have markers on the surface to detect incoming sensory molecules or trigger molecules, messenger molecules. Okay, not a bio class, but again, OChem is only interesting if we can figure out how to apply it. Bio can only be understood if you know the OChem. I'm going to say that over and over and over because it's what makes, I don't know, this is the first step of fused learning where you start getting other materials mixed in. Cell bio spoiler alert. So this is one of the cooler direct correlations between OChem and biochem. So here's a bigger picture of that cell membrane. Again, I emphasize the fact that that little gap there represents where the phospholipid, so you have glycerol, which has two alkyl groups coming off and a phosphate coming off one side, or whatever the polar head is. But these are now two tails coming off. So it's a little bit different than the previous picture. You have this scenario, and depending on the pi bond, so one of the things we are going to learn is that a double bond, because it is planar, is not very flexible. So because it's sp2 hybridized and it has this p orbital, it cannot bend. If we have only sp3 hybridization, then this thing is free to move around as much as it wants. So it could contort into that configuration. It could configure like that. It can keep on changing its shape. So what this ultimately means, if it is a flexible molecule, then it can twist and turn and pack together really tightly. The better it can pack, the more it's like a solid. That's that whole melting point, boiling point phenomenon. So the stronger the molecular forces, the lower the melting point, the lower the boiling point. I'm sorry, the higher, excuse me. So it's more solid-like. So I'm going to tell you flexible molecule equals better packing. They come together more tightly. Better packing equals higher melting point, which means it's more like a solid. So you've heard of the term saturated and unsaturated fats. So I want to emphasize, whenever you hear a word like that, sometimes it's not helpful by itself, but if you add one or two more words, it suddenly becomes more useful. So I'm going to tell you, every time you hear the word saturated or unsaturated, I want you to add the phrase with hydrogens. Saturated with hydrogens, unsaturated with hydrogens. What that means, if I consider just the simplest case, ones we did earlier, this is a double bond and is C2H4. If I have only sigma bonds, then it's C2H6. So if you have more H's, if you're saturated with H's, then you have single bonds, everything sigma, no pi bonds. So it's very flexible. So saturated molecules are going to be more flexible because everything's sp3, which means they pack better and they have a higher melting point and they're solids. So saturated fats are the bad ones because they can clog, they act like a solid. Conversely, unsaturated fats, because they have a double bond, they're not as flexible, they don't pack as well, so they typically are liquid-like. So if you have a liquid-based oil, it is most likely an unsaturated fat. And if you have a solid, like butter, for instance, it is a saturated fat. So just emphasize just the fact that the more H's you have, the more saturated you are. Okay, so I'm going to clear what I've written. And when into cholesterol, just mention again, cholesterol, this molecule, again, these are carbons at every point. So it's this massive molecule, carbon-based. You have one tiny OH and all these carbon, which means it is water insoluble. It does not go into water very easily. So to get it through the bloodstream, we need LDLs, low density lipoproteins, basically micelles to help transport it. It goes into cell membranes, sends its message, comes out. Cholesterol is just one of many so-called steroid or androstenedione-based structures that we use for messenger molecules biologically. But eventually, cholesterol is going to break down, get oxidized, and you still have this mess. And because urine is water-based, you cannot pee out this waste. So it has to go solid. Now, this is, I mean, may sound like too much information, bioinformation, or just disgusting, but you have to get rid of it. So generally speaking, not always, but generally speaking, water-soluble waste, urine, water insoluble or lipid-soluble waste has to go into solid disposal. Okay, so consequently, cholesterol gets oxidized and turned into something called cholic acid. It's a little more water-friendly, but it is still water insoluble. So if it aggregates together, you get all this molecule, this one with another one that all come together. But on the outside, it's water friendly. So you can make a solid chunk, all these solids come together, but on the outside have it interact with water. So almost like a micelle of sorts that will interact with water so that you could have a solid chunk with water friendly surface slide through somewhere that, let's see, what would we call a place that has broken down cholesterol to form cholic acid? I don't know, maybe the colon. I think it's actually completely coincidental that the terms are related, but who knows? Maybe there is some connection where somebody misspelled something and made it a name in bio. But cholic acid, the byproduct or waste product of cholesterol, is a chunk that can travel through the colon. So just random point of interest. Again, water versus lipid solubility, absolutely essential to understand in bio and chemistry both. Every molecule that goes in your body, you have to consider its pathway from where it starts to where it finishes. And there is guaranteed to be a water-friendly hydrophilic region and a water-unfriendly or hydrophobic region that it has to travel through, including exiting our body as well. So water solubility, pretty dang important as far as biology goes. Okay, lots of information. This had a significant bio component. Hopefully, this is where it starts to get a little bit interesting. We'll go into more detail class-wise in this. This is just a precursory introduction, but hopefully it's enjoyable. So I will see you at the next podcast. Thank you. Bye.